Hello, everyone. Since I'm in the middle of travel, I have to give these lectures online. So hopefully you got the same learning experience. So we will continue from where we stopped the last time. So just a little bit of recap of what we have learned the last time is basically is um, the two routing algorithm, right? So one is link state routing algorithm, which is Dijkstra's algorithm, and second is distance vector algorithm, which is Bellman-Ford algorithm, and we learn in great depths how they calculate the shortest path from a specific source node to or the destination node, and that's a very important. You have to make sure that you understand all the details of the algorithms. And in this slide, what we will continue is brief comparisons between the link state algorithms and distant vector algorithms. So we will compare it in three different dimensions. The first dimension we want to compare is message complexity, which means that in order to get this shortest path message calculated, this router inside the network, they needed to keep exchanging a lot of information, right? So that, for example, the link cost and their neighbors, distance vector, everything. So needed to exchange information. For link state algorithm, remember that we each node needed to do flooding. So all the it needs to send all the nodes inside the network about the neighbors, its cost to its neighbors. So it's kind of small information to a lot of nodes. So the message could be quite a number. So specifically is approximately big O and E messages has to be sent. For distant vectors, exchanges between the neighbors is kind of constant, right? So it's kind of you have to, if you have see anything changes, you have to recalculate your dissonant vector and propagate the new dissonant vectors to your neighbor. So it's kind of take a long time to converge, and the converge time actually varies depending on how big the network is, how much time it to spend converging. So right. And in terms of speed convergence, then these two algorithms also differ. So specifically for link state, the convergence is all about flooding. As long as all the node got the link of the whole complete graph's link cost, then they can do these local Dijkstra's algorithms. So they don't have to take a long time. And as we discussed, the Dijkstra's algorithms, the worst case is big O n square, right? And the drawback is that link states may have oscillation problems we discussed previously. And for the distant vector, the convergence time really is not predictable. It's dependent on the true case. For example, we mentioned that good news may travel very fast, but bad news may travel very slow, right? And also, if you have a routing loops, then it will be much more complex, right? And then the counting to infinity problem. So that's the same thing as the bad news goes slow, right? And in terms of robustness, both of these algorithms has its issues. For example, for routing state, link state algorithm, the nodes, it is possible that the nodes can advertise incorrect link cost, right? So because by default our algorithm is trust everyone, is flooding the accurate link cost to everyone. But in a lot of cases, it's like if you have some malicious node, then it will be difficult, right? And because we require that each node calculate is your own routing table locally, so by default you have to trust whatever the other nodes send it to you. So you get the graph and then calculate the shortest path. For distant vector algorithm, it's also possible that distant vectors node, these nodes may not advertise the accurate path cost. So in such table, it can cause inaccurate or more functions of the routers, because it's kind of ripple. There's kind of rippling effect, because if one node cannot get their distance vectors calculated accurately, then the result will be propagated to the neighbor and the neighbors to neighbor. So it's really kind of disaster situation in that specific case. All right. So that's a brief comparison between these two algorithms. So the next topic we are going to cover is about hierarchical routing. So as we said, if we do Dashes algorithm, or if we do this distance vectors, if the network size is so big, then it will take large. For example, for link state, it will take huge amount of flooding messages to be sent, right? But for the distance vector, it will span a huge amount of times for conversion, because distance vector messages only kind of exchanged among neighbors. It takes time to propagate it to the very end of the network. So when the network goes very big, then both of these algorithms will have problems. And specifically for the real cases, we know that the internet is so huge, right? So big that it is, if you treat the network as a flat network, and every routers are all identical routers, it's really will create a problem. So specifically, if we have like 600 million destinations in the network, and if you treat them as individuals, it's really will create a scalability problem. You simply cannot store all the destination addresses in all the routing table. It's too much, right? And also, this routing table needs to keep exchanging this reachability information with each other. That can be a huge amount of bandwidth consumption as well, data transmission. So the ideas is quite straightforward. I mean, regarding addressing these kind of scalability issues, the ideas is we can do kind of hierarchical routing things. In other words, we can divide the network domains into individual functional unit, or we call it autonomous system, or administrative, or some kind of domain. So for example, AMSO, we can have AMSO domain, right? AT&T has AT&T domain. So, and we further network this kind of autonomous system or individual domain together. So it's essentially to create a network of networks, a big network of many networks. So by doing this, each of these network, for example, AMSO network, you can have your own administrator. You can decide whatever routing protocol you want to use, algorithm you want to use, but you have no effect to the outside world. I mean, which means that essentially you can design your own network at your wish. It has no effect to the outside. All right, and you have full control of your own administrative domain. That's a good thing, right? And so that's the basic idea. We aggregate routers into regions. So such a region or domain, we call it autonomous system or AS. Okay, and any router inside the same autonomous systems, you can run the same routing protocol. Okay, for example, you can use RIP, you can use OSPF. It's totally up to you. So you use this algorithm only for inside this domain's routing, right? So essentially, it means that you have full control of your own domain. You can choose whatever routing protocol you want, depending on your own demands. And however, we do need to interconnect these different autonomous systems, right? By using gateway router. So gateway router is something like at the edge of these autonomous systems. So for example, AMSO, the outgoing, we have gateway routers, right? So when we do trace route commands in class, earlier in this semester, you can see that we goes to some kind of Great Plain or Mizzou's router, right? So there's the edge router at the end of our AMSO's autonomous systems, and is connected to the other autonomous systems, right? So by doing this, we essentially create a hierarchical structure. So we have intra-AS, or the other name is called intra-domain. So basically mean this is the domain routing things inside your own domain, like AMSO, right? And inter-AS or inter-domain, it means routing among different automated systems. So it's kind of, we are dividing this routing function into two levels. So inside the same automated system, you do intra-domain or intra-AS routing. Among these different automated systems, you do inter-domain or inter-AS routing. Very straightforward, right? And it's very good in terms of scalability. And it's very useful, right? So this is a rough view of the internet hierarchy. So it's, as I mentioned, it's roughly a hierarchical structure in which you have the top tiers is like top one, tier one ISPs like AT&T, Charter, AT&T, Sprint, Verizon, those big national ISPs, and beyond and below that, kind of regional ISPs. All right. For example, Charter is one of the regional ISPs, and the stub network are at the edge of this, or at the bottom of this hierarchy. So in which, for example, AMSO could be one of these stub network. Potentially, you can connect it to multiple automated systems or service providers on top of you for multi-homing, right? So each of these actually blocks right here represent as individual automated systems, individual domain, right? And inside the same automated system, we mentioned that we can run OSPF, we can run any intra-domain routing, right? But among these different nodes, all right, domains right here, then we needed to run this inter-domain routing protocol. So as the protocols, which is a de facto inter-domain routing protocol, is called BGP, Border Gateway Protocol. So which means that all the inter-domain routing in the current internet is carried out by the BGP. It's very famous, all right, for inter-domain routing. So by doing this hierarchical routing, we essentially needed to figure out some kind of solutions. Specifically, for example, you have to, for a specific route inside a specific domain, the forwarding table actually has to be decided by both the intra-domain routing algorithm and the inter-domain routing algorithm. Why? It's because you don't know, I mean, if you have any users connected to this route, you don't know the destination address is, right? If the user is sending a packet inside your own domain, you just need an intra-domain routing algorithm to tell you where to send, right? But if the destination address is some, for example, a Google address, then you may have to send it to the right border gateway, right? Either it's 1C or 1B, so that it can be relayed by AS2 or AS3 to the Google server, right? That part needed to be handled by inter-domain routing algorithm. So in other words, both the inter-domain and the intra-domain routing algorithm will decide the overall forwarding table inside this router, right? For example, if you external destination, then it needed to be handled by both. You have to know, first you have to forward this from this router to 1C or to 1B, and then 1B or 1C needed to know how to forward it to the outside peering this gateway, right? So it's kind of for external destination, both inter and intra will kick in. But for internal destinations, you just intra-domain routing will be sufficient. Make sense? So let's suppose a specific network scenario, right, Liz? So we have AS1, AS2, AS3 connected, all right, multiple networks. Um, so we want to understand the interdomain routing tasks. So supposedly, for example, we AS domain AS1s receive the datagrams with the destination address outside of AS1. So you may have to decide where to forward your packet to, right? Either you go to AS3 or you go to AS2, but which one? So basically, the autonomous system one must decide, for example, for a specific range of these destinations, they can handle it by AS3, right? For the other specific range of prefix or IP addresses, uh, they, they can be handled by AS2, right? You need to decide and you need to know and propagate this information, this reachability information to every router, right, inside this autonomous system, um, so that no matter who receive this kind of external destination addresses packet, they can be thrown to the right or to the correct routers to be handled next step. So it's kind of job of interdomain routing has to do, right? Decided which one can be reached by S3, which one can S2. Then you propagate this information to everyone inside your domain. Very straightforward, right? So that's the interdomain routing's job. So basically, let's suppose that if we have um, this autonomous system one, this router 1D, suppose it received a datagram. All right, but before that, we suppose that AS1 and AS3 is kind of all connected to AS1. So we know by using interdomain routing protocol, we know that, okay, we have a subnet X with address range. All right. So somehow through interdomain routing protocol, AS3 tell AS1 that AS3 can handle any destination address X, the packet with destination address falling into this range. AS3 can handle for AS1. All right, but not from AS2. So AS2 will not telling AS1 that it can handle X. So whenever this information is propagated and told to AS1, then AS1 is responsible to propagate this information to all the internal router in this domain, right? And for the specific router 1D that receives this datagram, it will determine immediately which next hop or which destination, internal destination router should this router forward to. So in these specific cases, it needed to find the least cost path to the border edge which connecting to AS3, because we know that we have to throw the packet to AS3, right? So AS3 is directly connected to 1C, which means that for this router 1D, you needed to install forwarding table entries saying that, okay, if I see address X ranges, then I needed to go through this port, right? So this interface is I, outgoing interface is I, which lead to this border gateway, right? 1C. The next step will be through to S3. So it's needed to be installed in this router 1D. So this kind of cases is kind of straightforward, right? So just interdomain tell you intradomain, and intradomain you make the forwarding table and just to execute the policy. But there's the issues if that in reality, if for example X, this kind of range of IP addresses can be reached, this subnet can be reached from both AS3 and AS2, and the interdomain routing protocol will tell both of this information to AS1. So AS1 now know that, okay, for this destination, both list pass and list pass will work. Then what to do? You have to make decision, right? You cannot forward the 2 copy because you have to take the shortest path. But this is interdomain. You don't know the overall shortest path is because every automated system only know your own message, right? You can calculate the shortest path for your own inside your own domain, but if you are running across many autonomous systems, you really have no idea which is the shortest path. All right. So in these specific cases, you have to make decisions. So when router 1D receives this packet with the destination addresses falling to X, then you have to decide that either you need to send it to 1C, right, or you send it to 1B through AS2. So this is actually the interdomains routing protocol's job to telling you this. So actually, what happens is we usually, in this kind of scenarios, when we face these decisions, either go to 1C or 1B, what we would do is instead of trying to figure out global shortest path, instead we do local optimal routing. So this kind of things, protocol or this routing is called hot potato routing. So hot potato routing is something that if you are, for example, you have a hot potato on your hand, you try to throw it away as soon as possible, right? So what hot potato routing does in these specific cases, you just send the packet towards the closest of the 2 gateway router, right? So for example, you know that 1C can lead to X, you know 1B can lead to X. So which criteria do you want to use to decide that you choose 1C or 1B? So what actually you do is hot potato routing, which means that you just see from 1D to 1C, from 1D to 1B, which one is the shorter path, simply for this hop. So if you see 1C is the shorter path, you throw to 1C. If 1B, this is the shorter cost, then you throw to 1B. Right? You don't care about the foreign cost, foreign steps. Right? So you just consider these 2 things. You just try to make these local optimal decisions. Right? So this is hot potato routing. So basically what happens is, first thing you need to learn the reachability informations and know that X can be reachable through multiple gateway, and then you use this routing information from the intra-AS domain to determine the least path to each of these gateway, compare these 2 options, right? And you do hot potato routing and choose one, choose a gateway that has shorter or least or the least cost, right? So and throw your packet. You added 1 forwarding table entries to that router 1D, and you install that one, and then the following packet will be forwarded around that path, right? So this is a hot potato routing. You make local optimal decisions and try to throw it out as soon as possible. Okay, so hot potato routing is very important. That is a very good, useful concept. So we know that to handle this interdomain routing, we need interdomain routing protocol, right? So for example, this automated system actually, you would have to exchange information. For example, for X, right? X, you have to AS1's AS3 has to tell AS1 that AS3 can handle X for AS1, right? So they kind of needed to keep exchanging these reachability informations with each other, so information is propagated. For example, if X is reachable through AS3, and AS3 will tell S1 that it is reachable to X1 to X, and then this information is further propagated to AS2. So AS2 know that, okay, to reach X, it can throw it to S1, and S1 can throw it to S3, and S3 can deliver that, right? So in reality, this kind of exchanging of the reachability information among different autonomous systems in a lot of cases is not just only about technical factor, like if it's the shortest path, if it is the least cost, right? Lowest latency or something like that. It's a lot of cases is decided by economic factors or even political factors. Like, for example, you don't want your packet to be routed by enemy country, right? You want to circumvent them for your safety, right? And also for economic, you definitely do not want to choose some very expensive routes when you have cheaper one, right? So, and you have to, for example, if you have your ISP, which is your provider, then you have to rely on him. So basically, this routing, interdomain routing, mostly is a policy routing. It's not the shortest path of something. In a lot of cases, it's policy routing. Decided, and this policy can be decided by economic or political factors. So you decided which prefix you want to announce to the outside or which you don't want to announce to the outside. For the prefix you announce to the outside, it means that you are willing to take care for them, right? So it's kind of a very natural solution. So policy is very important in deciding the interdomain routing decisions. So in reality, a specific ISP, for example, Verizon or AT&T, their network can be huge, right? It's like a nationwide huge network. So in some cases, one single autonomous system is still not enough. You want to divide it and use multiple autonomous systems to cover your huge network. Which is obvious because for AT&T network, although we do hierarchical routing, one specific OSP can still be very big. So it would be wise to divide it further into interconnected small-sized autonomous systems, and you connected them together, right? So a specific ISP can have one or more autonomous systems, right? So it's specifically the cases for big tier 1 ISPs. But for customer or the stub autonomous systems like Amazon, for example, this kind of customer network usually are located at the bottom or the leaf nodes of the hierarchy, right, of the tree. So in these cases, you possibly will have just one autonomous systems number allocated for you. So this is called a stub autonomous systems, which means you are at the edge, right? You are not providing service to anyone else. You are relying on this ISP serving for you. So you are purely a customer network. And in a lot of cases, this stub network or this customer network like AMSOS, you can choose to connect it to more than one ISP's network. So there are reasons for doing this. For example, AMSO, you may connect it one line. You can open one line to AT&T, the other to Verizon. So the reasons is that if you are providing very critical services, not like AMSO, but if it's a stock company, right? So they do these high-speed transactions. So if they lost the connections, then the business loss could be huge, tremendous. So they want to provide consistent connections. So even one of the connection is down, one of the service providers link is down, so you can still use the other one. So it provides some kind of multi-homing functions or load balancing functions or load spreading functions or failover functions among these different links that you are using simultaneously, which is very normal nowadays. Make sense? So this slide is a brief summary on the hierarchical routing we discussed. So what we figure out, because the internet has a scalability issue, because when the network is too big, simply cannot put them into the same autonomous systems, because doing flooding and this convergence will take forever, right? So to solve this problem, what we do is we divide this network into all these networks into autonomous systems, and we can do internal routings by using inter-domain routing protocol, and we can do this routing across multiple autonomous systems, and we do it by using inter-domain routing, right? So we can have both efficiency and flexibility. And you provide you can do this policy-based routing for security, right? So you can do have more freedoms and you can control in your own domain. That's great things, and it is very successful hierarchical routing. All right. So then, after we discussed at least the basic algorithm things, so in 4.6, what we're gonna discuss is the real routing protocol. RIP, OSPF, and BGP. So RIP, as I mentioned, is a typical distance vector routing algorithm. OSPF is a typical link state routing protocol. BGP is used for inter-domain routing, right? So we will discuss a little bit about it. So, so this is something I mentioned. The full names for the routing information protocol, RIP, and the full name of the open shortest path, OSPF. All right, so it's the distance vector, link state algorithms, and the BGP is called border gateway protocol. So remember these abbreviations; they are very important. Three kind of typical routing protocol. Now I'm running on internet every day, every moment. So these slides give you a deeper views of what's inside a specific autonomous system. So a specific autonomous system, as I mentioned, you can have many routers inside your autonomous system. For example, in this autonomous system, on the left-hand side, is we have 4 routers. They connected with each other, right? So they're connecting these subnets. So between these routers, they run this. You see these red arrows. They are intra-domain routing, right? Intra-domain links, right? And among these routers, the edge routers connecting these two domains, and they are exterior link. You have to run exterior routing protocol, right? Similarly, the case, the right-hand side case, it's can have interior connections, exterior connections, interior protocols, exterior protocols, right? Very straightforward. So depending on the functions, there are some other names. For example, if we are using for interior routing, then it's called IRP, interior routing protocol. For example, IRP and OSPF are 2 of them, right? So there are also some, but they are kind of obsolete. So all you need to remember are these 3: IRP, OSPF, BGP. Right? BGP is a typical exterior routing protocol, right? There are also some others, but they are obsolete. All right, so you don't have to care about it. There are for history reasons, there are more than these 3, right? But some of them just didn't survive. So this interior routing protocol, in some cases, also called interior gateway protocol. I know that a lot of names, but you seriously do not have to worry about it. You simply needed to worry about IP, OSPF, and IGRP possibly, because it's private, belongs to Cisco, so we have no ideas how they do it. They are not releasing their own document, so we don't have to worry about that. We just focus on IP and OSPF, right? So for the IP protocols, we mentioned that it is distance vector, so routing protocol. So it's originally invented in 1982, which was included in the BSD Unix distributions. So the distance metric used in this IP protocol, we know that it is a distance vector algorithm, right? So we needed to define the distance metrics. So in RIP, The metric is these numbers of hops. So maximally you can have 15 hops. So each link has cost 1. So essentially it means that the cost that you just based on how many hops from the source to the destination, you simply want to find the link or the path that has the least numbers of hops, right? Because each link has cost 1, right? So which means that you want to find the shortest path. It means you want to find the path with shortest numbers of hops, right? And the distance vectors, because it's distance vector algorithm, then they needed to exchange, the neighbor need to exchange this distance vector every 30 seconds by using some advertisement or response messages. And each of the advertisement you can provide up to 25 destination subnets. All right, so which means you can exchange every update. You can exchange 25 vectors, 25 destinations, right? So a typical network, for example, in this scenario, as shown at the bottom of this network, or of this graph, of this slides, is like this. All right. So basically, if we use hop as the metric, then we know, we just count how many hops you have to go through from a source to a destination. For example, if we are router A right here, right? So if you received an IP packet with a destination address of foreign to you, right? This subnet range. Then so what you would do, you simply deliver it, right? So it's just one hop. You deliver it right away, right? So if the destination address is subnet V, then you need to do 1, 2, right? So it takes 2 hops to deliver it. W similar as V, so it takes 2 hops, right? So if the destination is C, is X, for example, then you can count 1, 2, 3. It takes 3 hops, right? Similarly, it's Y. If the destination address is Z, then you can see 1 hop, 2 hop, right? So that's why it's. So you can simply depend on how many hops, because each of the hop you count it as link cost of 1. So, right? So the hops is actually decide the overall distance metrics. So if you want to find the shortest path, you simply find the shortest, the path with shortest, smallest numbers of hops, right? So a simple examples is of the routing information protocols is that if we have such a network, so we have router A, B, C, D, A, D, B, right? So in a whole line. So in the middle we have multiple is subnet connected. All right. So original information is like this. So you can see the routing table of this router D. What it has is if router D see the destination addresses fall into the range of W, so what it should do is the next router should be A, because it needs to throw to A and then deliver it, right? So it's gonna take 1 hop, 2 hop, right? So you can see the next hop is A, hops numbers to the destination is 2. Makes sense, right? So the first entry makes sense. The second entry is apparently you need to deliver to B, right? So next hop will be B, and destination hop will be 1, 2, right? So the second entry is also makes sense. So if the destination is Z, so supposedly that we have to, because by using this this kind of exchange this reachability information between D and B, then you will know to reach D that you have to deliver to B first, next hop, and then the hops supposedly is 7. All right, because in the middle there may be many the other nodes, 6, right? 5 or 6 other hops routers. And if you deliver to X, then it's direct deliver 1 hop, right? You don't have to throw it to the next router, because X is directly connected to this router D. direct delivery. So now, supposedly, something happened, and we have some kind of router C connected, and somehow you exchange this reachability informations and using distance vectors. Um, and somehow um, A find, for example, C tells A that it has another path, and this path information will be propagated to A, and A further propagated to D, right? Remember the distance vector algorithms? We keep in exchanging this distance vector propagated, right? So if you have better, if you have a good news, you have a better path, you will eventually propagate this kind of information. And if it's good news, its propagation is pretty fast. So in this case, what it essentially have, and what A tells D is that to reach the destination Z, actually A can go through C, which takes 4 hops, right? Which means from A to Z, it has to go through C, takes 4 hops. So D, then it will do local this Bellman-Ford equation calculation to see if that would be a better path. Remember the relaxation, the Bellman-Ford equation to see if it get a better value for you. So essentially what happens once you receive this good news, D will compare. And apparently, originally it's 7, right? To Z is 7. Now you have 4, which means that you add additional 1 hop. This is going to be 5, which means D find a new path to reach Z, which costs 5 instead of 7, which means it's a bad deal, right? This is a better deal. So which D will update its routing, recalculate based the Bellman-Ford equation and do relaxation, right? So correspondingly, this router D will update the destination routing entries for Z and update the next hop to A because A can handle it within just 4 plus 1, right? 5 hop to the destination Z. So which means original D goes through B, goes through this to reach Z. Now you have to go through A, goes to C, and then somehow it reaches to Z with shorter paths. Right? So this is a typical examples of distance vector algorithms and IP, how it works. In IP, the simple thing is that the distance vector, the cost is just about hops. It's kind of simplified, right? So what happens in what is designed in IP protocols is that if no advertisement heard after 180 seconds, so if no further advertisement, then you believe that link is done. It's gone, right? It's declared dead. And in that cases, then the route via that neighbor is invalidated. So the IP need to modify this local routing table and send advertisement to the other neighbors. So this is kind of counting to infinity problem, right? Even better news, it takes time for you to decide it is dead, and then you need to recalculate and send this new kind of distance effect to your neighbors. It takes time. And your neighbors will send further advertisement to its neighbors, right? So it's a typical counting to infinity problem. Because bad news goes slow, and if you use poison reverse, then you can prevent some ping pong loops, right? So that's kind of possible solutions. The apparently it's not perfect, as I mentioned before. So to run IP. On the router, what you have to do is you have to run an application level process on the router. Also, it is called a router daemon. Actually, this is a kind of application run on the router. It's kind of invisible to you because this router only handle layer 3 forwarding things, right? So this router D actually is doing its own business. It's not for your purposes. It's kind of a routing application run on the router. They are in charge of maintaining and exchanging this reachability information, and they get the routing, the shortest path, and the forwarding table, routing table figured out. All right. So you can see this kind of things is dedicated routing daemon run on these routers. And the advertisement, because they are applications, right? You have to decide to use UDP or TCP. So in IP, you use UDP, right? And periodically send this advertisement with each other, right here, right? So this route D actually is exchanging. It runs this routing. Gets the routing table calculated, and this is configured, and based on the routing table information, you turn it into forwarding table, and then the network uses this forwarding table to execute the routing decisions for every router, right? For every packet, right? So this application, remember, is only for router's own usage. It has no effect to your decisions, routing decision, and it will not read your own IP packet. Right? It's just for routing usage. So the second, the link state protocol is called OSPF. Or open shortest path first. So open means it's publicly available because it's not like Cisco's protocol. It's OSPF is free. Right? It's standardized by IETF, which means that everybody know how it works. Right? So it uses link state algorithms or dexterous algorithms, and because it's link state, then it means it has to do flooding, right? And the topology maps are kind of maintained at each of the node, and each node then do local calculation of the shortest path by using dexterous algorithms. So we have mentioned a lot of times is how this link state algorithm works. So I will not repeat again. All right. So for OSPF, the advertisement carry only one entries per neighbor, and this advertisement flooded to the entire automated system, which means advertised to everyone. For example, if AMSO is running OSPF, then each of these routers need to flood to all the other routers. And one small difference of OSPF with IP is OSPF to run directly over IP, right? So it's kind of different from the previous one. So in IP, it's use application. They run on UDP, right? UDP runs on IP, but OSPF directly run over IP. It does not. It's not an application level daemon or something like that. It uses networking, right? Directly encapsulating to IP. So it does not use TCP or UDP. So there's also another shortest path, which is ISS routing. Is very similar to OSPF, so we will not mention that. And OSPF actually is more advanced, and it provides more features compared with IP. IP is very simple, right? So it's kind of, as I mentioned, the cost is simply decided by the hops. But hops, usually it's not a good idea because it's, you pick the shortest, the least hops, but least hops does not mean shortest path, right? For example, one hop may be taking a long time, but if you go the other routes, even though the numbers of hops is increased, but the overall cost may be lower, right? The latency or delay may be lower. You never know. But IP does not differentiate these kind of things, right? So in other words, in OSPF, one of the benefit or features it provides is that it allows multiple same cost paths. But in IP, it's only one, right? And you can define multiple cost metrics, as I mentioned, right? That's great because you can decide your routing based on different metrics. Either it's money cost or the latency or bandwidth, whatever cost you want to define based on your own need. And the security is handled better by in OSPF because messages can be authenticated to prevent this malicious intrusion, but IP has nothing in this regard. And it also provides unicast and multicast support. Multicast OSPF or OSPF is provided, but it's not required. I'm not going to teach you about it, but if you are interested, you can do Google's search and you can find plenty of these standard documents telling you about it. All right. So if the domain is large, you can further, in a specific OSPF domain, you can further divide it into separate OSPF domains. So, hierarchical is always a good way to go. So if you consider this scalability issue, if you have a still domain, automated system domain is still too large, you can divide them into hierarchical OSPF domain, right? So it's kind of a very useful feature. So this one exactly tell you what is hierarchical OSPF. If a specific domain is too big, for example, this blue area essentially is individual domain automated systems, right? But because we have so many numbers of routers, since we decided that we can do hierarchical OSPF. In this specific cases, we have two level, all right? We have one area, second area, third area, and each of these areas is an individual OSPF domain. And at the edge of this, you will have area border router. It's not a BGP router, but it is area border OSPF routers. All right. So, which means that for example, if you have internal kind of communications, you don't have to go to the backbone routers or the boundary routers if the information is just exchanged inside the same area. So the same thing as the hierarchical automated system structure, right? So it's basically isolate these domains, and you can do your own routing, and the propagations, exchange of information only happens in your own area, unless you are running the destination running across different areas. Then in that case, it needs to be handled by the backbone routers, or if you are talking to the outside world, then it will be further handled by these boundary routers. Right? So it totally makes sense. So by doing these hierarchical divisions, the link state advertisement will only limited in each of these areas, right? And you only needed to know the direction, the shortest path to nets in the other areas. So, and if they can handle, for example, from this router, you can go through this path, and you will be handled by this backbone router that are interconnecting multiple these areas. So after the IP and OSPF, IP and OSPF, they are all for the same automated system, right? So the next very important protocol is BGP. As I said, it is inter-domain routing protocol, and de facto inter-domain routing is like glue that holds the internet together. So which means essentially put all these individual automated systems together. So inside the same automated system, you run iBGP, internal BGP, or interior BGP. And among these different automated systems, we run eBGP, or external links, right? So we define, for BGP, we have iBGP and eBGP depending on these two entities, or this router is run on this link. They belongs to this two different automated systems, or they belongs to the same automated systems, right? So what BGP does, as I said, they needed to exchange the reachability information for all these prefixes or the destination addresses, right? And following some policy. So economic policy or the political policy. So basically, what it advertises and what it tells the rest of the internet is, I'm here. Right? So it's kind of, they allowed this automated system to exchange that, okay, for this throw it to me, I can handle. So they are telling each other and exchanging all this information. So we have IBGP and we have eBGP. All right. So between any autonomous systems, they needed to establish this BGP session among these peers. For example, in this 3A, 1C, or 2A, 1B, they needed to run these BGP sessions because they needed to establish this stable, these kind of sessions. They exchange this reachability information. For example, to guarantee that it's reliable transmission exchange of this information, we use TCP for the BGP sessions. And what the BGP does is it advertises these passes to different destination network prefixes, right? Basically, it's telling passes. For example, in previous examples, we have X connect to S3, S3 tell S1, S1 tell S2, right? So it's like how this autonomous system by autonomous system, you know the approximate paths to the destination network prefixes. So this protocol BGP is also called path vector protocol. It's not a distance vector because distance vector is used inside the same subnet or inside the same domain, right? This is a path vector, which means you are telling the overall path, but this vector is used for across these autonomous systems, across domains, right? It's not used inside the same autonomous systems, right? So what happens is that, for example, AS3 advertises a specific prefix to S1. What it is essentially telling S1 is that I promise to handle all the packet with that destination addresses of this prefix. So which means that it's the guarantee, it's a commitment that if you want to deliver a packet to that prefix, throw it to me. So this is a promise in these BGP messages. And if you have multiple kind of IP addresses or IP address ranges, then you can aggregate these prefixes and send it in advertisement. So this advertisement can be short, right? So the address aggregations we have discussed a lot. So I'm not going to repeat it right here. So it's very useful, right? We can reduce the size of these BGP messages. So in these specific cases, it's exchange these things. So these slides show you the differences between eBGP session and IBGP session. So the solid links is right here run across different autonomous systems, eBGP sessions. All right. So inside each of these domain, you run IBGP sessions. So remember, both of them run TCP. Right. So they are kind of keep exchanging this information. So for example, for this 1C, what it does is it can use IBGP to distribute whatever new prefix information to all the routers inside the same autonomous system, right? And it has use eBGP to exchange information with the other autonomous systems that pairing with it, right? For example, 3A. So by doing this, for example, 1C got the this advertised, and then 1B can re-advertise the new reachability information to S2 across this link, right? So that by keep doing this exchanging through eBGP, IBGP, and eBGP again, so this overall reachability information is exchanged among these different autonomous systems. So whenever a router learns a new prefix, it will have to create entries for the prefix inside its folding table. Okay. So let's finish these slides. So to define a specific route, the BGP needed to exchange information. So what it essentially exchange is called BGP attribute. So a specific attribute is kind of, um, you know, there are two sorts of attribute information. So one is AS path, basically telling you to reach a specific prefix which approximate which AS numbers you need to go through. It's like a path, not in the sense of each router's path, but how many ultimate systems you have to go through. So each of the ultimate systems has a number, right? So you have to go through this AS first and then next. So it's the AS path, high level path. And then next hop is telling you the specific internal routers to the next hop AS. Right, so it's kind of the edge routers that leading to the next ultimate systems. Right, so these are the two attributes that you have to kind of include in any BGP entries. All right, so a specific route actually consists of a prefix, which is the range of the address, right, and plus the attribute, which means what you are gonna do if you see this prefix. So each of the route or routing entry in the BGP table actually tell you, for example, if you see these prefixes, then you go through this AS path, which means you have to throw it to this path first, and this is AS first, right? And then it's not only telling you the big picture or the road maps of AS path, it also tell you what's the next hop, which is the intermediate exiting edge router that is connected to the next AS on your road map. Right? It totally makes sense. So by using this information, you know exactly how to handle a specific packet with the destination prefix fall into this range. Right? The prefix plus attribute is routes, which telling you what to do for each of the prefixes. And the gateway router receives the route advertisement. You will have to use import policy to either accept or decline the request. And by doing this, actually, you can execute your policies, right? So it's basically, as I mentioned, interdomain routing is a policy-based routing. If somebody requests you to handle for a specific, for example, your enemy's network address, you will decline it, right? Because you don't want to do it, right? So it's kind of very straightforward. You need to use this policy and enforce this policy so that it's kind of interdomain routing. You can decide what to do and what not to do. It's fully under your control. All right, so that's call it a day, and I will see you Thursday. Thank you so much for attending this.